All right, so in the last few videos, we saw some applications of ordinary differential equations of the first order, right? So all of the material we did was prior to the midterm, and the applications were all dealing with first order differential equations, meaning the highest derivative that you ever saw in those problems were the first derivative. So now what we want to do is we want to move to differential equations of the second order, right? And we're going to talk a little bit about this, and we're building up. I wish we could stay in application work. There's a lot of other things I'd like to be able to show you in applications for first order differential equations, but we saw a few, and now I want to be able to show you some more applications. But we need some more skills because now we're dealing with second order differential equations. Okay, so let's start with, notice for equation 1, I'm going to refer to equation 1 and equation 2 throughout this section. Basically, equation 2 is going to be the one I'm going to refer to for this video. But starting with equation 1, this is a second order differential equation. Okay, notice that you do have a second derivative as your highest derivative in the equation. Now, this f of t that it's equal to, we're gonna start with the homogeneous form of this, right? So in other words, we're gonna set that equal to 0. That's how we get to equation 2. Of course, the caveat is a cannot be 0 because that should make perfect sense, because if you have a coefficient attached to your second derivative as 0, then you don't have a second order differential equation, right? So, but how do we do this? So we're going to be dealing with the homogeneous form of the equation 1. So it's going to always be set equal to 0 for this video. And what do we want? Well, we want to talk about the solutions to these second order homogeneous linear differential equations, right? So I know that's a mouthful, but that is what we are trying to do. Now, I want to start by making an observation, and then I'll try to generalize that observation. So, kind of follow me along here. So imagine that I solved this equation for my second derivative, right? So I would bring my b plus y prime and my c plus y to the other side of the equation, or I can just bring my second derivative, a y double prime, to the right side. But let me write that. Okay, don't worry about the negative symbol. That's not what's of importance right now. I want to go ahead and write. So I would have b, say by prime plus c times y, and if I solve, I would have a y double prime, and now I can negative a. I'm sorry. Let me go ahead and give myself some space here. It's equal to negative a over y double prime. Now I can go ahead and divide by negative a, right? If you really want me to. So this would be b over negative a y prime plus c over negative a y is equal to y double prime. But I want to generalize what property solutions to these types of equations have. Ready? So can we agree that I have solved my second derivative? Okay. Then can you and I then agree that I should be able to get to my second derivative by a linear combination of my first derivative and y, right? I can add up some constant times y prime plus some constant times y should get me to my second derivative. Well, that is the property that I'm talking about here. The solutions to these, now these are ordinary, but second order homogeneous linear differential equations have a special property, if you will, and that property is that the second derivative is expressible as a linear combination of the first derivative and the zeroth derivative. Now the zeroth derivative just means y, right? You didn't take a derivative yet. So, all right, now, if the first thing that we should start to consider, right, is, wait a minute, what type of functions out there, right? What type of functions out there would have a property where I can, take the first derivative, take the second derivative, but then be able to reach the second derivative through a linear combination of the original function and its first derivative? Well, the form that comes to mind, right, and the form that comes to mind for y, what would y have to look like? Well, I'm hoping that you're at least thinking about e to the x type of functions, right? Because the derivative of e to the x is e to the x, and the second derivative of e to the x would still be e to the x. So notice how the form of this function looks like it would lend itself here. And in fact, I'm just going to go ahead and get us to where we need to be. It is true that now I'm not going to use x in this case, but I'm going to say functions of the form e to the rt are exactly the form that we're going to want our solutions to take on. And let me kind of show you what I'm talking about here. So let me grab this. Actually, I don't need the caveat, so let me just grab this. See if I can take it with me. And let me go ahead and park that right here. Beautiful. Okay, so I'm going to go ahead and get rid of how I box this in here, so it just doesn't bother me. So you just entertain yourself for just a second. And now let me do something. Let me park this somewhere. Okay, so as I mentioned, the form of the solutions is going to be this y is equal to ERT. And now what I'm going to do is I'm going to go through and take the first derivative of y. Then I'm going to take the second derivative of y. And then I'm going to plug them in to this homogeneous second order differential equation. Okay, you ready? So we're gonna take the derivatives. These derivatives are going to be with respect to t. Ready? Let's do this. So if you take the derivative of e to the rt with respect to t, that's just chain rule. So you would let u be rt. The derivative of u would be r. So you with me that the first derivative would be r e to the power of rt. And what would the second derivative look like? Well, that's again, if you use chain rule for e to the rt, that's going to be r times r, or r squared e to the rt. And do me a favor, don't fast forward, don't skip ahead, because it's going to be important to know what's happening here. So what I'm going to do is I'm going to plug this in, each of these in the right spot. And then you're going to see what comes out of this is the crux of this section, right? It won't take me very long at all. So after I plug in, I would have A times r squared e to the rt plus b times r e to the rt plus c times e to the rt, and all of that must equal 0. Okay. Now, what comes next is the key. So I'm going to factor out this e to the rt. And now notice what's left. What's left is a times r squared plus b times r plus c. And now, let me pose the question to you. Is it possible for e to the power of rt to ever become 0? No. Does that make sense to you? No matter what you choose for r or t, you're not going to get e to the power of rt to ever equal 0. So you can think of it as I'm dividing that out. I'm going to lose that e to the rt, and what we're left with is simply a quadratic equation. ar squared plus b times r plus c is equal to 0. Now, I'm going to give this a name. Okay, and you're going to hear me refer to this often. This is what we call the auxiliary equation. Okay, or characteristic equation. You might hear me refer to it as either one of them. So this ar squared plus b times r plus c is equal to 0. This is the auxiliary equation or the characteristic equation, and I want you to think about something here. So what that means is that for our solutions to take the form of e to the rt, that will only be true in situations where the r satisfies this auxiliary or characteristic equation. I'm going to say that one more time. So we talked about y equals e to the rt is the form of the solution. But that is only going to be true, right? That's an if and only if statement. That's only going to be true if r satisfies this quadratic equation. And now I want to take a second and talk about what type of solutions can come out of a quadratic equation, right? So this, I'm probably going to have to grab another page. Nope, I'm actually not. So now clearly if you have, when you have a quadratic equation, like ar squared plus b times r plus c. Did I write that? I think I tried to move that around and it didn't come out very well. Let me try to write that a little bit better. So ar squared plus br plus c. So anytime you have a quadratic equation, the types of solutions that can come out of a quadratic equation are going to depend on these coefficients A, B, and C, right? So, in fact, let's go a little bit farther. Notice that inside the square root of b squared minus 4ac, now that we refer to that as the discriminant, right? So, but notice that here's three different scenarios. B squared minus 4 times A times C. Right, there's three different scenarios here. Well, if B squared minus 4 times A times C, I'm so sorry, when I rush, I have to slow down to make sure I give myself enough space and I don't write anything silly. B squared minus 4 times A times C. Okay, so let's start with the first case. What if B squared minus 4AC is greater than 0? Right? If it's greater than 0, what type of solutions would you expect? Well, if it's greater than 0, you would be taking the square root of, right? So that you would be taking the square root of some number that's greater than 0. And that would tell me that we're going to still have real solutions, right? We're not going to be dealing with complex numbers. We would still have real numbers. And in fact, how many solutions would you get? You would have two both real and distinct solutions. That's important that you stay with me on this, okay? Because each of these three cases is, if I can recall, it's its own section in the book, right? It's possible maybe two of them are in one section and the third is in the other. But the first case is if you have a positive number inside the square root, then you would have two distinct real solutions. Now, what if it's the case where your b squared minus 4ac is actually a negative number? What if it's less than 0? Well, then you're definitely going to have imaginary units, right? In your solutions. Your solutions are you're going to have what we call complex numbers, right? Complex numbers, complex conjugates. For solutions. And then finally, what if it actually equals 0? Well, you of course you can take the square root of 0, right? That's not, you don't need imaginary units to be able to do that. You don't need complex numbers. But in a scenario where your discriminant is equal to 0, then you're going to have real number solutions where your r sub 1 is going to equal your r sub 2. I think that makes sense. If I plug a 0 in for my radical, then I end up with negative b over 2a and for r1, and I also end up with negative b over 2a for r sub 2, right? It doesn't matter about the plus 0 or minus 0. It all zeroes out. So we're going to begin with the first scenario. That is when your auxiliary equation, your characteristic equation, the discriminant, the b squared minus 4ac, is producing numbers that are greater than 0. Okay? So if you've been waiting, maybe you've even fast forward. Let's get to the example and you can reverse engineer the theory from the example. No problem. Ready? You want to find a pair of solutions to the following second order differential equation. All right, so I'm going to go through this the way I would go through it. I would start by identifying A, B, and C. In this case, A is going to be equal to 1, B is going to be equal to 5, and C is going to be equal to -6. All right, now, recall that the auxiliary equation is AR squared plus B times R plus C. But what I'm going to do here is, since I know that A is 1, B is 5, and C is -6, you can think of it as, let me rewrite this auxiliary equation as by plugging in for A, B, and C. Are you ready? So you can imagine I'm just going to plug in for A, plug in for B, plug in for C. So in that case, we have R squared plus 5R minus 6 equals 0. Now this is the auxiliary equation for example 1. Okay, now they were nice to us. This one actually factors nice and easy. So I'm going to go factor it out. So this would be R minus 1 multiplied by R plus 6 is equal to 0. And this tells me that R, let's say R sub 1 in this case, I'll tell you what I'll do. I won't do that yet. So in this case, R is going to be equal to 1 or -6. With me so far? Okay. So what that means is, let's go back to the general form of the solutions. Remember, y is equal to e to the power of RT. Right, this is the form. So in this case, we're looking for a pair of solutions, and the pair of solutions would be, we're gonna let R sub 1 equal 1, and then we're gonna let R sub 2 equal to -6, and now let's just plug in, we're gonna plug each of these in to the equation y, the form of the equation, and that's going to produce the following set pair of solutions. We would have e to the power of t, and we would have e to the power of -6t. Okay, so now what we have to keep in mind is that we are done. Those are a pair of solutions to that second order differential equation, but that is one of many, right? So in this particular case, you have to, let me show you what the general solution is going to look like. So what I'm going to write now, the general solution for the second order differential equations, these homogeneous equations that we're dealing with now, the general solution is always going to look like this. So y of t is going to be equal to c sub 1 e to the power of R sub 1 t plus c sub 2 times e to the power of r sub 2 t. Okay, now, we were not asked to do this, but I'm going to go ahead and produce the general solution to example 1, right? All we were asked to do was find a pair of solutions. Well, we did that. But now I'm going to produce the general solution to example 1. So in this case, y of t would be equal to c sub 1 e to the, now r sub 1 is equal to 1, so this would be e to the power of t plus c sub 2 times e to the power of, in this case, r sub 2 is negative 6, so this would be negative 6t. All right, so that would be the general solution to the second order differential equation for example 1. Now, where we're going to go from here is we're going to do example 2, which is an initial value problem. And what we're going to be able to, I'm going to walk through this yet without making any claims. But what I'm going to be able to show you probably in the following video is that we can rest assured that although for general solutions like we just wrote, there are an infinite amount of answers, right? There's a whole family of answers to that equation. We can rest assured that these techniques can and will produce a solution, right? A solution, a true solution to a second order differential equation, meaning one that is both unique and obviously exists, right? But is also unique. So how do we begin this problem? So I'm going to, for right now, I'm going to go ahead and park this y of 0 equals 0, y prime of 0 is equal to negative 1. I'm going to kind of park this off to the side for just a second. And I'm going to walk through the solution process the same way that we did in example 1, right? So how did we do that? Well, we first started off by noting that in this case, a is equal to 1, b is equal to 2, and c is equal to negative 1. All right? Now, remember the original auxiliary equation is ar squared plus br plus c equals 0. So in this case, we're going to go ahead and plug in for a, b, and c. So that gets me to r squared plus 2r minus 1 is equal to 0. And again, just keeping track of our vocabulary, what is that? That's your auxiliary equation. Okay. Now, the goal right now is to solve for r. Now, in this case, this is not going to factor, right? So since this is not going to factor, you would have to use the quadratic formula. So I'm going to go ahead and give you the two solutions. So r sub 1 is going to equal and r sub 2 equals. Let me write the solutions, and then off to the right, I'll tell you that we had to use the quadratic formula. So negative 1 plus the square root of 2 and negative 1 minus the square root of 2. these are the two roots, the two solutions, and we use the quadratic formula. By the way, if you're ever bored, since you're on the internet anyway, you should Google. Many of you probably know the quadratic formula by heart. You should Google the cubic formula or the quartic formula, and think, what if my teacher, maybe my high school teacher, made us solve not just the quadratic, using the quadratic equation. What if we had to use the quartic or the cubic equation? Anyway, good luck. So, by the way, there's nothing higher than that. There's no equations to solve for roots beyond the fourth degree. But nevertheless, so let's go ahead and form the general solution right now. Okay, so I'm going to start with y of t is equal to c sub 1 times e to the r sub 1 t plus c sub 2 times e to the r sub 2 t. This is the general form. And all we're going to do is just plug in for r sub 2 and plug in for r sub 1, and then we'll have the general equation, the general solution to example 2. That's not good enough. That's not what they wanted us to do, but that's where we'll be. So in this case, y of t would be equal to c sub 1 times e. Let me use some parentheses here. So r sub 1 is negative 1 plus the square root of 2 times t. All right, let me go ahead and give me some space, plus c sub 2 e to the power of, now it's negative 1 minus the square root of 2 t. All right, so that is the general solution. That is a whole family of solutions. But at this stage, it's time to go back and use these conditions, these initial values. And the initial values were, say, y of 0 is equal to 0. And we were told that y prime of 0 is equal to negative 1. Right? These were the initial conditions of whatever system, whatever problem we're dealing with. Okay. Now, what we're going to need to do is we're going to need to figure out, and I'll go ahead and tell you right now, that normally when you're moving to a particular solution like we are right now, you're normally going to have to use a system of equations. So let me go ahead and start with y of 0 is equal to 0. Okay, now how do you interpret that? So that means that when you plug 0 in for t, you should get back out 0 for y. So what's going to happen right now is I'm going to take this general form, I'm going to plug zeros in for the t's, and I'm going to make y equal to 0. Ready? So let's do that. So I have 0 is going to be equal to c sub 1 times e. Now, do you agree with me? I think I can make this a lot easier. Do you agree with me that when I plug 0 in for t, the entire exponent zeroes out, so that's e to the power of 0, plus c sub 2, and again, plugging 0 in for t causes the entire exponent to zero out. Now, e to the power of 0 is simply 1, so here's the first equation that's going to be in our system. So we have c sub 1 times 1 is just c sub 1 plus c sub 2 times 1 is just c sub 2. So I'm going to go ahead and box that in. Now I'm going to go to the next page, and what I'm going to take with me to this next page is going to be this general form, this condition dealing with the y prime, and I'm going to need this first equation in our system. So I don't think I have enough room. Nope. So let me go ahead and give myself enough room. And now I will ask you just to entertain yourself for a second so that I can write the information that was on the previous page. I don't know if I should be talking with you, so there's not this it's not this white noise in the background, this deafness of me being silent, but I guess I'll just babble. How's that? That way it's uncomfortable because I'm babbling, but it's not just silent. So I needed that. I also needed y prime of 0, which was equal to, let me double check, I think it was -1. Yep. Equal to -1. And I also had c sub 1 plus c sub 2 was equal to 0. Okay, so each of these little parts is needed. Okay. So if you can imagine what I need to do at this stage is, if you can kind of follow me here. So I have one more condition, and that's that I need to plug 0 in for t into the first derivative. And then I need to set the first derivative equal to -1. But are you with me that I don't have the first derivative? So I would actually have to take the first derivative, y prime, of what I'm circling right now. And this is not incredibly hard, but it's hard enough that that you would have to, it's tedious enough that you should slow down when you're doing it. I'm just going to go ahead and tell you what y prime is, okay, because it's just a derivative. So y prime of t, and I'm going to try my best to write small enough but have enough space. Are you ready? So this is what the derivative of y would look like. So we would have -1 plus the square root of 2 times c sub 1 e to the power of -1 plus the square root of 2 t. All right, plus, all right, let's, now it would be -1 minus the square root of 2, c sub 2, e to the power of, do I have enough space? -1 minus the square root of 2 t. Okay. All right, ready? So at this stage, I finally have the derivative of y. Now let me just make sure I didn't make any silly mistakes while I was talking out loud. Well, none jump out at me. So what I'm going to be doing right now is plugging the 0 in for t, and I'm going to be setting the first derivative equal to -1. So the good news is all of this, since t is going to be 0, is going to become 1. Right? Does that make sense? So let me go ahead and produce that now. So in this case, I'm going to have -1 is equal to -1 plus the square root of 2 c sub 1. I do hope that you're with me on how all of that became 1. If you plug a 0 in for t, that would be e to the power of 0, which is just 1. Plus -1 minus the square root of 2, c sub 2. Okay. So at this stage, what I'm going to be doing is, because I need to go from general solution to particular solution, I need to know what c sub 1 and c sub 2 are. So I'm going to take the following two equations, set up a system, solve the system. Ready? Let me do that now. So let me take 0 is equal to c sub 1 plus c sub 2. All right, so there's your system. All right, so if you want to solve the system, what you're going to need to do is, well, you can, I mean, it's up to you how you want to approach it. You can multiply that. Let me just go ahead and write what I'm about to do, right? You can multiply equation 1. Actually, in this case, I'm sorry, I wrote it on my paper. This equation 2 by one plus the square root of 2. Does that make sense to what I'm trying to tell you here? That if I take this, so this is my equation 2. If I take equation 2 and I multiply that by 1 plus the square root of 2, that's going to help me cancel the c sub 2's. Okay, so obviously 0 times 1 plus the square root of 2 will remain 0, but I'm going to have a 1 plus the square root of 2 here, and I'm going to have a 1 plus the square root of 2 here. So that's going to be 1 plus the square root of 2 and 1 plus the square root of 2. So are you with me that when you add those, the -1 and the positive 1 are going to zero out, and the negative square root of 2 and the positive square root of 2 are going to zero out. That leaves you with the canceling of c sub 2. All right, so let's figure out what we have when we add. So -1 plus 0 is -1, and that's going to be equal to, so now I have -1 plus 1 is going to zero out, but I have a square root of 2 and another square root of 2, so it's going to be equal to 2 square roots of 2 c sub 1. All right, beautiful. So I went from a system of 2 equations, 2 variables, to a system of 1 equation, 1 variable, and now I can figure out, if I divide by 2 square roots of 2, then I finally can figure out that c sub 1 is going to be equal to -1 over 2 square roots of 2. Okay, so you will never see, if you look at the answers in the back of the book, you're never going to see radicals in the denominator. Not that there's anything wrong with having radicals in the denominator. It's just you're not going to see them produce answers in this fashion. So I want you to understand that if you just multiply, what they're going to rationalize the denominator. So if the back of the book, the textbook would say multiply by, say, the square root of 2 over 2 times the square. I think I may have mispronounced that. They're going to rationalize by multiplying the top and the bottom by 2 square roots of 2. Right? I hope you understand that this is just a fancy way of writing the number 1. 2 square roots of 2 divided by 2 square roots of 2 is just 1. So it's a fancy way of writing 1. So that's going to be equal to 2 square roots of 2 over 8. Let me forget my negative symbol. Which you can reduce to negative square root of 2 over 4. All right. So at this stage, I'm going to go ahead and get us to the answer. You can now you know what C sub 1 is. You can plug C sub 1 back in to one of the equations above it to solve for C sub 2. And you would find that C sub 2 is going to be equal to, you guessed it, positive square root of 2 over 4. So at this stage, again, you have done so much amazing work, but let's not be sloppy, okay? The job is for you to produce the particular solution to the initial value problem, right? You just have a bunch of work, good work, but a bunch of work on your paper. You need to form the answer, because I'm now going to just plug everything back into the general solution. So I think the best thing for me to do is to go ahead and clear this board. Okay, if you need to pause it, you pause it. But I'm going to clear everything out except my answers. And I'm going to go ahead and plug in for C sub 1 and plug in for C sub 2. Ready? So I have negative square root of 2 over 4 plus, and then C sub 2 is the square root of 2 over 4. That is the particular solution to the initial value problem. Here's what I'm going to do, since we need to move on, and I'm going to go ahead and conclude this video in just a second. Here, let me do something for you though. Let me give you a problem very similar to what we just did, and I will, when I come back in the next video, I'm just going to give you the solution. I'm not actually going to walk through the scenario, but assume that you have, let me go ahead and, let's assume that you have y, this is what I want you to try on your own. Let's say you have y double prime minus 2y prime minus 2y is equal to 0. And you have the initial conditions that z of 0 is 0, and y of 0 is 0, and y prime of 0 is equal to 3. Now, what you're staring at is very similar to example 2. And I want you to see if you can solve this initial value problem, okay, using the techniques that we just used. When I come back in the next video, all I'm going to do is produce the answer. I'm not going to tell you the how, but it's the only way to get good at math is to do some math. So I will see you in the next video.